So when we are gathering information from a proportion, we use a slightly different standard error. That's this P1 minus P over N. And depending on our confidence interval, we can figure out, as I mentioned at the end of class last time, a margin of error. Now, the margin of error assumes two things. It assumes that my probability of occurrence, my chance P, is as big as it can get, and it assumes that I'm going to use a 95% confidence interval. Now, the reason we assume 1/2 is because when we use 0.5, that's the biggest possible value for P times 1 over P. The value P equals 1/2 is the maximum of that product. Why do I need to know the confidence interval is 95%? Because that's where I get the z-score from. What z-score goes with 95%? Say again? 1.96. So if I want the margin of error itself is 1.96. Only depends on n. It only depends on how many people I'm going to ask. And that's why I can make the statement, and the table that we see on page 296, that the number of people needed to decrease my error goes up by the square of how fast I want that to go down. If I want a margin of error to go down a lot, I need a lot more people. Suppose I ask 250 people. What's my margin of error in this case? Say again? Yeah, that's the assumption all the time with a 95% confidence. Based off of what I'm seeing in the table on page 296, I think the answer should be somewhere in the 6-ish range. What do you get? 0.0619. Sounds good to me. Notice 1/2, 1 minus 1/2. That's 1/2 times 1/2 here on the top. Square root goes all the way down. So now it's just calculator driven. You can't see squat there because of the light. 0.0, now that's a percentage. This particular survey of 250 people would tell me I have a margin of error of 6.2%. If I do 1,000 people, what happens here? I would hope so, because we're going to divide by something bigger. But I went from 250 to 1,000, right? How much bigger is 1,000 than 250? In multiplicative terms, it's 4 times bigger, right? Square root of 4 is 2. If I do 1,000 people, all I have in this calculation is to change that 250 to 1,000. My margin of error is cut in half, a factor of 2. But I had to ask 4 times as many people. If I want to cut it in half again, I've got to go to 2,000 people. No, I've got to go to 4,000 people. I have to use the square because I'm taking a square root here. And this is why a margin of error around 3% is common for all the polls I'm hearing on the news about the presidential election. What percentage of people are going to vote for candidate A or B with a margin of error of, because they're only surveying about 1,000 people. If I use a different confidence interval, then I'm going to have to use a z other than 1.96. But the assumption for a margin of error is that we're doing a 95% confidence interval. Questions? Now, margin of error takes into account the fact that there are errors in my survey, biases, and simple random errors, both of which can happen through no fault of my own. We talked about that back in chapter 3. What if I do a bunch of surveys, or I look at a bunch of events, or I want to know how often is this going to happen, and I do the trial like we were doing Bernoulli trials, right? I do the experiment a certain number of times, and it never happens. Well, then I would say that P is 0. If P is 0, then my margin of error should be 0. That doesn't make a damn bit of sense. If I have not had any occurrences of my event in, I don't know, 17 trials, then the chance of my event having any occurrence has been 0. I've had 0 out of 17. There's got to be some way to figure the error. But the error here comes from the number of trials rather than the actual event itself. So if I'd had 17 trials, I look at 17 medical records. On a given day, I go down to the maternity ward and I look at the 17 kids that were born, and every single one had at least some complication. It could have been anything from a low APGAR score to the mother needed a C-section to something weird happened, some complication. So I would say the chance of having no complications is 0. What's my error? Well, it might not actually be 0. It might be fairly small, though. Without any actual occurrence, I use that upper limit for the confidence interval. So what is the value of 3 over n in this case? That's not a small number, is it? What'd you get, 100? Yeah. A 17.6% chance is a lot bigger than 0, isn't it? Now, I'm 95% certain that the correct proportion, if I looked at all the births at the hospital or all the births in the country, or I looked at all the births possible in the world, the chance of having a birth without complication is somewhere between 0 and this number. So I'm pretty sure the right answer is somewhere between 0 and 17.6. And if I do more trials, that number goes down. But it goes down faster because there's no square root in the bottom this time. Questions? We started talking about means and proportions. We were talking about taking a sample. We had a definition way back, chapter 1 and 2, where we said, how do we know if a population is effectively infinite? Not truly infinite, but effectively infinite. You've got the textbook in front of you. You can turn to the index in the back and look up the phrase effectively infinite and see where it shows up. Might have to look up population. Page 35. If the sample is less than 5% of the population, we assume that it is effectively infinite. But if I have a small population, if I wanted to sample from this class, 6, 7, 8, 9, 10, 11, 12. There are only 20 of you in the room. 5% means 1. I'm going to take a sample from this class. One of you is going to be a representative for the whole class. How that person does is the average for this course. You guys are in deep shit. That's a horrible idea, isn't it? So if I have a finite population, then my sample size is bigger than 5%. Or if I sample with replacement, let's say I pick somebody from the class, then I put that record back in the pile, and I could pick the same person more than once, right? If I wanted 7 people from this course, pick one, put it back, stir up the pot, pick one. I might pick the same person more than once. That's what happens, and that's sampling with replacement. How do I account for that in all of these calculations of error? Now, there are several different methods for calculating where you repeatedly sample, where you sample with replacement. A lot of these are called bootstrapping methods, but they involve how you take the sample. I want to do this in the calculation instead. We have something called the finite population control factor. Square root of capital N minus little n. Wait a minute. Capital N is the population size. Little n is the sample size over capital N minus 1. So if I'm sampling out of a very large population, these two numbers will be fairly close together. But if I'm sampling out of a small population, these two numbers will be different. And what this does is it reduces my margin of error because that number is less than 1. Because I'm sampling from a larger fraction of the population, this makes my margin of error smaller. So how does that work? Well, remember we're doing one of 3 calculations for a mean, where I know the standard deviation. I use the z-table. And then I use my standard error, sigma over square root of n. But I'm going to make that smaller, so I multiply by my control factor. A really crappy looking z there. But that's where I know the standard deviation. If I don't know the standard deviation, then I can't use z. I have to use t. And that's where I use s instead of sigma. But again, I multiply by the same reduction formula. If I'm doing a proportion, I use my margin of error calculation here. But then I multiply by my control factor. So this is a way to shrink your margin of error. Because you're sampling more often or from a larger percentage of the population, you get away with figuring out, oh, this adjustment narrows the range because I took more of my sample, more of my population in my sample. Let's do that first one. Let's suppose I have a mean of 50 and a known population standard deviation of 15. And I had a population of 1,000 people, but I took a sample of 90 of them. Gesundheit. What's my sample proportion? Little n over capital N. Aha. That's too big a proportion to be effectively infinite. So I need to use one of my corrected versions to find a confidence interval for this mean. Somebody pick a confidence level. 90, 95, or 99? Okay, if I'm finding a 95% confidence interval, I go back up here and I say, oh, a mean with a known standard deviation. That's this formula right here at the top. I need the z-value. If you flip back to Appendix D in the back of the book, we want the z that goes with 0.025. Why that? Half of the 5 that was left for my 95. You said 95%. What's left over is 5. That's my confidence level. That's alpha. Half of that is where I get the z-value from. But for 95%, that's the same z-value we've been using this whole time. That's 1.96. So now I can figure out this number, and then I can add or subtract to my mean to get the confidence interval I want. So scroll that right off the top. I have x bar minus z alpha over 2 sigma over root n, and then my correction factor, and then I have plus the same expression. And this will be my interval. So the standard deviation given to me in the problem was 15. The z-value, 1.96 from our confidence level. The population is 1,000, but the sample is 90. So the sample size goes here. But now inside this square root, population minus sample over population minus 1. And then the same numbers go here. And all of this, at this point, is now to churn through your calculator. So I'm going to multiply these numbers out. 1.96 times 15 divided by the square root of 90 times the square root of, and now this whole thing, 100 minus 90 is 910. I'm sorry, 1,000 minus 90. 1,000 minus 1 is 999. Let's go 4 decimal places because that's usually what shows up in the back of the book. 2.9578. So now my confidence interval is 50 minus 2.9578 and 50 plus 2.9578. if I had not used the correction factor, if you just multiply 1.96 by 15 and divide by the square root of 90, what do you get? Aha! Which is bigger than this, isn't it? This is the uncorrected margin of error. If I didn't know whether or not my population was finite, that would be the one I was using. If they hadn't given me the population size. But by taking a larger fraction of my population as a sample, I get a better estimate, and thus my margin of error can be smaller. Questions? When you are doing surveys, when you are doing the data analysis, you'll be asked, hey, how big was the population you pulled from? I don't know. What are you going to be working in? What is your future business career going to be doing? Maybe you will have a very small sample for a very large population. Maybe you'll never need this. Maybe you'll be looking at a very small sample of a very small population. If I asked you about the ages of the presidents, well, that's not a really big group, is it? There have only been 45 so far, right? 46. We don't have a huge number of presidents to work on. If I ask you to take a sample, you hit number 4, you've already hit 10% of the group. Oops. Most of the time, put that in air quotes, most of the time, we're going to work with populations that are large enough that this won't come into factor. But when it does, it changes the rules substantially enough that we need to be aware of it. So, quite frequently, the question asks, how many people do I need to sample? So somewhere in your survey design, in research methods, we'll talk about how big an error is acceptable for any given day, for any given problem. But let's say you want an error of 2% or 5% or 3%. You know the margin of error. Well then, if it's an infinite population, I don't need that correction factor. And our uncorrected margin of error is calculated right there, z times the standard deviation over the square root of n. I can't use a t-table here ever. Why not? Why can't I use t? Because we can't use t without degrees of freedom. Degrees of freedom depends on the size of n, and my goal is to figure out what n I need. Okay, people, algebra time. Take this equation in all the letters and solve for n. How do I get n all alone?
Multiplied by z, or I guess it'd be
This is why there is an Alex score and an algebra prerequisite for this course in general. But I need to do the algebra here.
first I brought the square root of m over e times square root of m equals z. And then divided by the e square root of m equals z times standard deviation of e. And then I gotta get rid of the square root, so I just n equals z standard deviation over e squared.
Perfect. Now, please note, what I need to have is what my confidence level is. So if I want a 1.96, a 95% confidence interval, I want a 99% confidence interval, I need the z value that goes with my confidence level. I also need sigma. I may or may not already know sigma. I could take a preliminary sample and use an estimate. I could make an assumption that I have a uniform distribution and use the sigma that I get from b minus a over the square root of 12, b minus a squared over 12, all square rooted. I could assume a normal distribution and say, oh, my high minus my low, that should be 6 standard deviations. I can estimate it that way. I can try lots of different things. Most of the time, if we're doing the survey from scratch, we'll have some preliminary sample. Oh, I asked 15 people. Now I can say, all right, based on that group, let's look at a larger sample. Suppose I do a preliminary sample, and in my preliminary sample, I have a mean of 65, and a sample standard deviation of 10. I can use that to estimate my other standard deviation. I want a 95% confidence interval for this mean. I want an error of plus or minus 4%. Oh, well, that's my E. I might as well use this as my estimate for sigma, and I'll come back to that. What Z am I using? Hot damn. 1.96. So, how many people do I need? Whatever answer you get here, round up. Always round up. Because I don't know how to do a fraction of a person, and I'd rather have one more person surveyed than one less person surveyed.
It's 4%. Why would it not be 0.04?
Because I've already taken that piece into account as a percentage in the margin of error calculation. The other reason is because I want this to be the same units as these. So it might not actually be 4%. It might be for, assuming these are percentages. If these are, errors of manufacturing, then this would be 4 errors in manufacturing. I want the units to be the same. So actually, I'm going to go back here and I'm going to say all of these are percentages so that my units match. What do we get here? Round it up, make it 25. Yes, ma'am. This is a number. This is just a number of people. How many do I need to sample? How many cars, how many people, how many whatever. That's a raw number. It doesn't actually have any units at all. You're welcome. And if you think about it here, percentage, inside my parentheses, the units canceled, and Z doesn't have any units either, does it? So these have the same unit, those units are gone. This never had any units. This whole number has no units on it at all. If I am doing a mean to estimate the sample size, I needed some sort of estimate on the standard deviation. What if I'm doing a proportion? We're just talking about voting preferences, right? That's not an average. That's who do people prefer by what percentages. That's a proportion. All right, wait a minute. In a proportion, this was my standard error. This square root of pi times 1 minus pi, well, those were our actual population proportion over n. Same problem. I want to know n. How do I get there from here? I got to go back through the same calculation. I'll square first this time. Square will get rid of the square root. I multiply by n to put the n over on the left side. Then I can divide by the e squared. Now again, this tells me how many people I need to sample for a given margin of error with a certain known confidence level. I'm in the same problem position. I need the proportion. How do I find it? I could do a preliminary sample. I could use historical data. But as I see in every financial and fiduciary announcement, past performance is no indication of future trends. I could make a guess. The biggest possible value for this comes if both of those numbers are 1/2. So if the proportion is 1/2, that'll give me the largest possible estimate here. And like we said earlier, that's why we assumed pi was 1/2 in our previous confidence interval calculation, because it made that as big as possible. In this case, this number is usually given as a percentage, isn't it? The chance of my event happening is usually a percent. Matt, this time, I do need this to get converted, this E, to a decimal. So if this is in percentages, if I write it as 9%, that's great. But if I write it as 0.09, then this needs to be written as 0.0 whatever. I need to be consistent. So if you write that the proportion is 5% and you use 5, well, which you're not going to, you're going to use 0.05, right? To do 1 minus, you're going to use the 0.0, then E needs to be 0.0 whatever. So if I tell you that my error is 2%, but my chance of success is 50%, then I write them both that way. And now you can tell me how many people I need. Now this time, I would again say, oh, we should round up. The textbook actually tells me not to round, and I think that's stupid because I don't know how to do 0.3 people. I would go with the same statement, round your numbers up when you're talking about people. Okay. A large overarching question. Why should I give a flying? All of this confidence interval comes down to one statement. I'm pretty sure the right answer is in here based on my sample. Now you go out and you take a sample. What's the chance your sample is way out there on the edges and not in this interval? Should be fairly small, right? But what you're going to be doing is testing whether or not you got the right number. That is our next chapter, hypothesis testing. That's where all of this comes together. Those of you in lab sciences, we do this a lot there. Business, a little less, but still a lot of questions about hypothesis testing come up in manufacture. I will see you all on Wednesday. Is that what day it is? Have a good one, everybody.